Hi, this is Math Kimchi, and today we will learn about geometrical probability. When we are finding normal probability, we usually find the number of successful outcomes and divide that by the number of total outcomes. This works really well most of the time, but when there are, for example, infinite possible outcomes, then the usual method will not work. One way to get around that is by using geometrical probability. And with geometrical probability, we find the area or length or volume of successful outcomes and divide that by the area, length, or volume of total outcomes. A problem without geometrical probability would be, what is the probability that a random integer larger than 0 and smaller than 10 is larger than 5? Here, there are a finite number of outcomes, and the total cases are 9, and there are 4 desired cases. And to find the probability, we just divide the desired by the total and get 4/9. If we were to change integer to number, then we wouldn't be able to count all of the possible cases since there are an infinite number of them. That's because there are an infinite number of numbers in between 0 and 10. So what we do now is we can create a diagram that contains all the numbers between 0 and 10. And the fact that 0 is here doesn't actually matter, since 0 is just one case. It's a finite number of cases, and since we are dealing with an infinite number of cases, it doesn't actually impact our probability. And the same goes for 10 and 5. This whole number line contains 0 to 10, as I said, and the red contains everything that is larger than 5 and smaller than 10. And this is our desired area, so everything in here is what we want, and everything that's here is what we don't want. The desired length is 5, and the total length is 10, so that means our probability is 5/10, or 1/2. For a two-dimensional problem we have, today Anthony and Billy will arrive separately at a library at a random time between 1 p.m. to 2 p.m. Anthony will stay at the library for 15 minutes, and Billy will stay for 15 minutes. What are the chances that they will be at the library at the same time at all today? And it would be good to use a two-dimensional graph for this problem, since there are two variables, which is when Anthony arrives and when Billy arrives. So this is the graph containing all of the possibilities of when Anthony and Billy arrives. And this is the total area, since we know that Anthony can only arrive from 1 to 2 p.m. and this is 1 p.m. and this is 2 p.m. And the same goes for Billy, where this is 1 p.m. and this is 2 p.m. And the condition that has to be met for the desired outcome is that A is less than B plus 15 and that B is less than A plus 15. When these two are met, we can know that the Anthony and Billy can meet. Now, if we graph A is less than B plus 15, we'll get the blue region, and B is less than A plus 15 results in the red region. The purple region is the area that meets both of the requirements, and this is our desired area. The total area is 3,600, and that is because 60 minutes and 60 minutes, if they're multiplied, we get 3,600, and the desired area, which is the purple, can be total minus the not desired. And once we solve that, we will get that the desired area is 1,575. Now, we need to find the probability by dividing the desired area by the total area, and that is 1,575 over 3,600. And when we simplify that, we get 7 over 16. Keep in mind that when we do this, we want to keep the units the same. So we could have multiplied 1 times 1 for the total area, where it was in terms of hours, but then we would have had to do the same for the desired area. For our final question, we have, what is the probability that if I break a stick in 2 random places, that the 3 pieces can form a triangle? And the hint is, in order for 3 sides to form a triangle, the sum of the length of any 2 sides must be larger than the length of the other side. And if I put this into inequalities, it would just be A plus B is greater than C, B plus C is greater than A, and A plus C is greater than B. And if you think you can solve this problem, try it on your own before continuing to watch this video. So, what we have here is the stick, and any of these points, anything on here can be a broken piece. And we are assuming that the stick has length 1 in some type of units. Now let's say we broke it into these 2 places, and now let's call the length of the broken point closest to 0 and 0 A, and the length of the broken point farthest to 0 and 0, let's call that B. And now we can have the length of the pieces, which is, this one is A, this one is B minus A, and finally this one is 1 minus B. And there are 2 variables, which is A and B, so we have a 2-dimensional graph like last time. One thing that's different is that this half of the graph cannot actually be possible because we decided that B is farther than A, and so B has to be greater than A. And so we can just get rid of this half as our total. And we also have that A and B are between 0 and 1. The conditions for the desired outcome is easy to find after we remember the side lengths, which is A, B minus A, and 1 minus B. Now let's create the three inequalities and simplify them. Remember to flip the sides when you multiply by negative numbers. Now we have B is greater than 1/2, A minus B is greater than a negative half, and A is less than 1/2. Now let's color code these to make it easier to solve and graph, and we will have that this center region here contains everything that can create a triangle. So this gray region is our desired area. The total area is equal to 1 times 1 over 2, so 1 times 1 over 2, which is 1/2, and the desired area is 1/2 times 1/2 over 2, which is 1/8. And to get the probability, we just divide 1/8 by 1/2, and we get 1/4. So the probability that if I break a stick into random places and the three pieces form a triangle is 1/4. And a problem to practice yourself is, today Anthony and Billy will arrive separately at the library at a random time between 1 p.m. to 2 p.m. Anthony will stay at the library for 15 minutes and Billy will stay for 20 minutes. What are the chances that they will be at the library at the same time at all today? This problem is similar to one we did earlier, but the time that Billy stays is changed to 20 minutes instead of 15. That's it for this video, and thanks for watching.